Welcome back. So last time we talked about centripetal force, and we said that that is any kind of center-directed force. Centripetal literally means center-directed. And what we wanted to know was, how fast can our robot take a turn, take a 90-degree turn, without flipping? Now, remember that that's going to depend upon the friction on the surface. If there was no friction, well, it's not going to be able to make that turn at all. So what is the maximum speed for a given amount of friction between the robot's tires and the surface that it's running on? What is that maximum speed that it can travel at and still make the turn without either flipping or skidding through the turn or anything like that? We're also going to take a look at centrifugal force, which is something you may have heard of, but doesn't actually exist. There's no such thing as centrifugal force. And so once we understand how centripetal force works, you're going to understand why centrifugal force is really just some sort of fictitious force. Let's get started. All right, so last time we derived this expression here for the centripetal force. And let's write it over here so we can make it a little bit bigger. So our centripetal force is going to equal the mass of the object that's turning times its along track velocity, its tangential velocity around the turn, divided by the radius of that turn, like that. And so here again, we're dealing with scalar magnitudes because my force, remember, as I go around this turn like this, my force direction is always changing depending upon which direction I'm pointing here. All right. So now we want to look at the idea of how fast can I go and still keep this robot on the ground. So let's draw our robot in the middle of its turn right here. Okay. So there's our robot, and it's turning, and it is turning in this direction. All right, so it's in the process of making its turn. Here's our center of the radius of curvature, so that's this r, and remember that that's going to be our distance from the center of this arc here. Now, notice that the inner wheels have a shorter radius, a shorter turn radius than the outer wheels do. So you see that the outer wheels have a much larger turn radius than the inner wheels. So given that, look at your expression here. Which side of the robot is going to feel a larger centripetal force? Think about it. So the inner wheels have a shorter r than the outer wheels. So as the radius goes down, what's going to happen to the centripetal force? It's going to go up there, inversely proportional. And so by the same token, if the r goes up, the force is going to go down. Either way, you end up with the same idea that the inner side of the robot is going to be what's going to experience the greater centripetal force. All right, so the frictional force must be at least as large as that so that it doesn't skid or flip or anything like that. So which side of the robot needs a larger frictional force to stay on the road? Well, since it's got a larger centripetal force on the inner side, it also must have more frictional force on the inner side. All right, so this puts us in the strange situation of, in order for my robot to stay on the road, it needs more frictional force here on the inside than it does on the outside from that. Well, but it doesn't have that. So if I have just enough frictional force for the outside wheels, what's going to happen? Well, now the inside wheels don't have enough friction force to stay on the road. And so my outer wheels stay on the road, but my inner wheels leave the road. And that's what causes the robot then to flip, or your car, if you make the turn too tight. So we're going to use that principle then to figure out how fast can I go without flipping. So first thing we need to do, we know it depends upon the friction. So go through your flip book and find the expression for the frictional force. Pause the video if you need to, but make sure that you've practiced being able to find that. All right, so we know that the frictional force is equal to a coefficient of friction times the normal force. And remember that these are scalar magnitudes because my normal force is not going to be in the same direction as my frictional force, so I cannot make them both vectors. Mu, though, can either be the coefficient of static friction or it can be the coefficient of kinetic friction. Which should it be in this case? Well, it's moving, right? So it's definitely going to be that coefficient of kinetic friction. So there's our force of friction. All right, so the other thing that we're going to need to think about is we're going to need an expression for the centripetal acceleration. Now, this is the centripetal force here. How can I get the centripetal acceleration? Well, do I have a constant mass? Sure, we hope the robot isn't losing any of its mass. So I know that for any given force, then, because we want just the centripetal part, so centripetal force must be equal to the mass times the centripetal acceleration. And we use an AC for that. So plug this expression in, set these two sides equal to each other, and see if you can come up with an expression for the centripetal acceleration. Pause the video, do that now. It shouldn't take you but a minute. Got it? All right, so we know that MAC is equal to mv squared over r. My masses cancel, and so I get AC is equal to v squared over r. And so that's my centripetal acceleration. Let's make sure that our units work. V squared is meters squared per second squared, but then I'm also going to divide by a meter, so that gets rid of one of those, and that leaves me with meters per second squared, which is in fact acceleration. So this is something new that you're going to want to add to your flipbook when you're looking at centripetal force. This is the centripetal acceleration. Remember, it might not be speeding up or slowing down. So that along track acceleration might be the magnitude of that might not be zero for the acceleration. However, my velocity vector is definitely changing. And so this acceleration, this centripetal acceleration, you can think of that as what's changing our velocity vector. So it's what's changing our direction in this case. All right, let's look on the next page. Now we're going to solve the scenario where we are trying to find that initial or that velocity that will safely get us around the track. So we said that the robot has a mass of 0.45 kilograms. It's going to make a 90-degree turn with a turn radius of 0.75 meters. So, and as we said, remember that this is measured from the robot to my center. And that's obviously, I've got to make sure that both sides can be measured, stay on the road. So really I'm looking at this radius that goes to my inner wheels. If I've got enough friction to keep my inner wheels on there, then I know that I'm going to have enough friction to keep my outer wheels on there as well. All right, so the coefficient between the robot's tires and the floor is 0.95. We want to know how fast the robot can travel and still make the turn without flipping over. So our scenario then is, if we're going to try to find how fast it's going, think about what we're actually looking for. We're looking for the along track velocity. So that along the magnitude of that is going to be its speed. So we're going to find the along track, the tangential velocity when the robot is turning. Right? And so this is going to be the maximum that we can have. So we're going to have our diagram here, and we're just basically going to have what we have over here. So here's my robot, and I know that this is R right here, and I know that it's moving with some velocity vt that I don't know what that is, and I also know that my mass of the robot is here. And so the last thing I know is that my coefficient of friction is given to me. All right. So we'll record all of these values down in our step 3 here in just a minute because we're a little short on space here. Okay, so when we're talking about the design, what are we going to do? Well, we know that the force of friction must be equal to the centripetal force, right? So we know that the force of friction must be equal to our centripetal force. If it's not, then our robot's going to flip. Okay, so we're going to use the definitions of our force of friction and our centripetal force, and we're going to solve for our tangential acceleration. All right, so that's our plan, and it's pretty straightforward. So let's go ahead and write down all our symbols. So R, we said, was 0.75 meters. UK we said was 0.95. Remember, that doesn't have units. The mass of our robot is going to be 0.45 kilograms. And what I'm looking for is VT, and I don't know what that is, but I know it has units of meters per second squared. So step 4, we're going to need our equations. Now, looking back to our step 2, we already decided that I need to set my force of friction equal to my centripetal force. So that's actually an equation. That's our condition for solving the problem with that. That's telling us what exactly we need. And this is similar to when we wanted to find the apogee height. Apogee height was defined to be when my j component of my velocity was 0. So here, my condition for staying on the track is that the force of friction is exactly equal to the centripetal force. All right, and then we said, well, okay, now we're just going to write down all of our other forces, so our definitions. So my force of friction then is going to be equal to mu k times F of n. And we know that our centripetal force then is going to equal mv squared. We'll go ahead and make that t so that we're clear on what we're looking for, divided by r. All right, now I've introduced a new symbol here. I need to know what the normal force is. So let's draw this from the side, since our normal force is going to be vertical. So here's our robot going around the turn. That's going to be my normal force. Now, ideally, it's neither sinking down into the road nor is it launching itself off. And remember, that's a possibility here. So what we want then is we want them to be in equilibrium. So we want the sum of the forces in our j hat direction to be 0, which is equal to the normal force. And we'll say that this way is j positive minus the gravitational force. And so that then tells me that the normal force is simply equal to the gravitational force, which is m times g. So there's our other equation for that. So our normal force is equal to m times the acceleration due to gravity. All right, so with that, we've got pretty much everything we need. So let's go ahead and solve it. So we'll start with our first equation here. I've got f of f is equal to fc. So I've used that one, can't use it again. Let's plug in our two values here. So I've got mu k f normal must be equal to m tangential velocity squared over r. So the other thing left then is to plug in for our normal force here. So I've got mu k times mg must equal m vt squared over r. All right, so I've used all my equations, so hopefully the problem is solved. So we want to solve for our vt, so I'm going to multiply both sides by r, and so I get r mu k. Now look at this, my m's actually cancel. So mu kg is equal to vt squared over r. Notice that this g now, f normal is equal to minus mg, so it's this scalar magnitude here. However, because I'm only going to be working with scalars in this equation, I can't have any positives or negative signs. I have to take the scalar magnitude even of the force, of the normal force as well. So that's kind of important. You're not going to have a negative sign in here. And if you tried to put a negative sign in here, we're going to see we're going to take the square root in just a minute. You'd end up taking the square root of a negative number, and you might go, wait a minute, that's weird, that shouldn't happen. Well, the reason is because both of this equation right here and this equation right here are scalar equations. They are not vector equations. So if I've got a scalar, then I lose all concept of positive or negative directions in there. Okay, so that gets rid of my r here, and I'm going to rewrite this one. So I've got vt squared is equal to mu k r g, and then I'm going to take the square root of both sides, and so finally I get, we'll just write it up here, that vt is equal to the square root of mu k times r times g. So solving it for this particular case, it's going to be the square root of 0.95, there's no units with that, times our radius of curvature, which was going to be 0.75 meters, times my gravitational acceleration, which is 9.81 meters per second squared. Remember, it's a scalar magnitude. Make sure my units work out. I'm going to get meters squared divided by seconds squared. Then I'm going to take the square root, and that'll give me meters per second. So that looks good. So pick up your calculator, and we get 0.95 times 0.75 times 9.81. And then don't forget to take the square root. And so we get that the tangential velocity needed to keep the robot from flipping is 2.64 meters per second. Now remember, anything less than that, then my force of friction is exceeding my centripetal force, and so I'm still fine. So this then represents the maximum turn speed. So this is the maximum speed on this surface, on this 0.95 coefficient of kinetic friction surface. So, and that's going to be our final answer. Now, that's actually very fast, right? Think about it. You're moving 2 meters, 2.5 meters every second. So there's a good chance then that our robot is going to be considerably slower than that. That's not going to be a problem. On the other hand, if I had a car, that might be a problem. And so I'm going to have to be very careful about how fast that I'm going as I move around that turn. All right, as we're saying, you may have noticed that the tracks in a like NASCAR race or whatever, they're banked at some angle, right? So that the normal force is going to be at some angle to the horizontal here. And the reason they do that is we want the total force that the car, in this case, experiences as it goes around the track to be equal to the normal force, to be in the same direction as the normal force. So you can see that if I don't have that angled here, then let's say that this is the ground and it's flat. My centripetal force is acting this way. My normal force, of course, is acting perpendicular. Now, normal force, and we also write this as N in that direction, they mean the same thing. One's just a shorter way of writing the same thing. We'll keep going with the normal force, the way we've written it here, but remember that N with a vector sign, not a hat, with a vector sign means exactly the same thing. And oftentimes you're going to see that because, well, we're lazy and it's easier to write. All right, so we need to find an expression for the angle between the normal force and the centripetal force. So let me just draw it over here. So here's my centripetal force, and here's my normal force, and here's my total force. And so we want to know, let's go ahead and measure it from the horizontal, since that's the way that makes the most sense. I want you to come up with an expression for that angle theta. And we give you the hint that you're going to need a right triangle. So we're going to need to slide one of these. Pause the video, work it out. Give me an expression for the angle in terms of the normal force and the centripetal force. Have you got it? All right, so we need that theta to be inside our triangle. So we're just going to slide over our Fn. These are still the same vector. All these are vectors because it's got the same magnitude in the same direction that it has over here. But now we can see which of the trig functions is going to give me theta. That's going to be tangent. So I know that the tangent of theta, and remember with this right triangle with the sides, we're talking about scalar magnitudes. So this is going to be Fn divided by Fc. Again, those are scalar magnitudes. All right, and so then to find the value of theta, theta is simply the arctangent of the normal force, the magnitude of the normal force, divided by the magnitude of the centripetal force. And that's all there is to it. So we'll write that down here of our normal force and our centripetal force. And so that also gives us the angle that we want this track to be banked at. And that way the normal force is going to be going, the total force is going to be going directly through the robot or the car, or whatever happens to be going around the turn. And now we've got the same amount of friction on both wheels. Do you see that that's the advantage that we're going? So looking at the robot from behind, you remember we had the inner wheels here and the outer wheels here. And the problem that we had was that the inner wheels were experiencing more centripetal force than the outer wheels, but now I've got the same amount of friction on both of them. Okay, so now we want to go ahead and substitute in what we know for the normal force and for the centripetal force, and let's get an equation then, or an expression for theta that depends upon our actual physical variables. So stop the video, pause the video, and let's work that out. You got it? All right, so let's plug in what we know here. We know that this is going to be the arctangent, and let's plug in our expression for the normal force, which in this case let's look at the general case right here. We know that our normal force had better be equal to our gravitational force, because the idea is we don't want the robot to go flying off the surface, and of course it's not going to sink into the surface. So if I'm writing my equilibrium, then this is in the j hat direction, we'll say that this is positive j hat here, then I want this to equal 0, so they're in equilibrium. That means I'm going to have a positive Fn. Now I've got my scalar magnitude minus my Fg, and so that tells me that Fn, the magnitude of Fn, is simply equal to the magnitude of Fg, which is mg. Notice that these are not vectors, because I have gotten rid of the vector sense of this by simply writing the sign of it in front of it. So I need the scalar form of Fn, and this is in fact a scalar. So don't get in here thinking that this is negative 9.81. It is not. This is the scalar magnitude of gravity, so it's just a number. It's just 9.81. Scalars have no concept of positive or negative. All right, so we've got that one. So then we know that this Fn is going to be mg. Now I need my centripetal force. Again, we'll write that here. And we decided that that was the mass times that tangential velocity divided by r. So let's put that in right here. And so we get m tangential velocity squared over r. Let's simplify things a little bit. Notice that my mass cancels. So it actually doesn't matter the mass of the vehicle. That's why we can build our track to one consistent theta, no matter what the weight of the cars is as they go around the track. So we've got a fraction here that we're going to flip and multiply. And so I get that the arctangent of g times r divided by v2 squared. And so that's going to be my final result then. So this tells me the angle at which I need to bank the track. All right, so now we're going to take a look at centrifugal force, this fictitious force. We're going to show you why it doesn't actually exist. Take a look at microtask 4, and let's suppose that you are riding in the passenger seat of this vehicle, and so this is you sitting right here, the little blue dot that you see. All right. According to Newton's first law of motion, if you started out moving forward, I'm not talking about the vehicle, we're talking about you, and you're moving with the car in this first diagram right here. So which direction would your body continue to move as the car turns? Well, there is currently no force acting on you, is there? So the centripetal force is acting on the car, but it's not acting on you. You don't have any friction. Your feet are not touching the ground as it comes in there. So your body wants to just keep moving in this forward direction, right? So your body here wants to move in the forward direction. So if the car is turning to the left, where would your body go? So let's make this a little bit bigger so that you can see what's going on. So this is you sitting here, and you want to go this way. But now the vehicle is actually turning. And so now you can see that you've actually effectively been pushed against the side of the wall here. It's not that there's any force pushing you there. It's simply that you want to keep moving, but the car is turning away from you. And so that's why you get pushed into that. So what's happening then is you're getting pushed against the right door here. Right? Now, this is the same principle behind centrifuge. If you've ever seen a ride at a fair or something, we've got something that's turning, and let's say it's turning this way. And let's say that you're sitting here, and so you're looking towards the center. As it starts to turn, you want to go, let's do this in red, you want to go this way, or at least your body does because of Newton's first law. However, there's a normal force that is acting this way. And you see that because it's center directed, in this case, the normal force is the centripetal force. That's not friction that's moving, it's actually the normal force of the wall. So because there is that normal force, that's causing this turn to go about. But your body wants to go straight forward. So you've experienced this force as being into the wall, when actually it's the wall pushing on you coming with that. So there's no force acting out this way. But your body can't perceive any kind of gravitational force or centripetal force. All that it can perceive is the normal force. So you're feeling the wall pushing against you. Same thing here. You're feeling yourself be pushed against it. You may say, well, wait a minute. I don't know if I'm making a turn. I feel that even if I'm not touching the wall, right? Well, that's because there's actually friction between your butt and the seat, right? So the seat is trying to move to the left. The friction is acting against you, and that's what you feel that your body is fighting against. So it's the same idea as if you had been actually hitting the door, except now it's just the friction of the seat. You want to go forward, the friction of the seat is keeping you in the car, but you're still feeling that force to the inside of the turn. And so this is why you feel this imaginary force to the outside. Your brain is programmed to think that, oh, I'm still going straight. And if you had closed all the windows and you couldn't see outside, let's say you're on a carnival ride or something, then if that turns, your body thinks that you're still going straight. Your brain thinks that you're still going straight. And so because you're actually trying to go forward, but the wall of that centrifuge or the car you're in is pushing you to the side, you say, oh, I'm feeling a force towards there, when in fact you're trying to go straight and the vehicle is what's turning. So don't let anybody fool you. There is no such thing as centrifugal force. Don't use it. It doesn't exist. You can't do any problems with it. There's nothing that you can do that will enable that to be something useful for you. Instead, it's the centripetal force. That's what's real. And you can see that force, this center-directed force, let's do that in blue, this center-directed force in all cases is what's causing this vehicle to turn. And so that is the actual force that's having a physical effect on you. All right, so now hopefully you have a better understanding of what centripetal force is and how it works. And we applied this to the example of the speed that you need to stay on the track, but centripetal force exists all throughout the world. And we mentioned in the first video one back that even gravity will act as a centripetal force if you're in orbit. It's any force that is directed towards the center of your turn. And you can think of that centripetal force as being the force which is changing your direction. That's the important thing. I may be, if I add some tangential acceleration, well, I'm just going to go faster. However, if I am changing my direction, then there must also be some sort of centripetal force acting on me. Also remember that centrifugal force doesn't exist. Wipe that from your mind. You really don't want to ever use that. It's just going to confuse you. It's going to have you have a lot of force vectors going in the wrong direction because it doesn't actually exist. So think about that. Try to integrate all of that as we start continuing our study of rotational motion, and we're going to get a little bit deeper into this idea of spinning. All right, we'll see you next time.